All right, let's take a look at question 3b. G of x equals x squared minus 3x plus 2 over x squared minus 1. As before, we're supposed to take a look at the x and the y-intercepts, the vertical horizontal asymptotes, and draw a sketch of this function. Let's start by factoring the numerator and the denominator. So we can factor the numerator, x squared minus 3x plus 2, as x minus 2, x minus 1, and we can factor the denominator as x plus 1, x minus 1. We could see that we could cancel the x minus 1 on the top and the x minus 1 on the bottom, except we can't do that at x equals 1. So if we write this is equal to x minus 2 over x plus 1, we definitely have to put a caveat there to make it true, except at x equals 1. Now we've radically simplified this thing. So we can already see that this curve has a hole in it at x equals 1. We were able to cancel this. Let's take a look at the x and the y-intercepts. So for the x-intercept, let's say for the y-intercepts, we'll set x equal to 0. So y is equal to 0 minus 2 over 0 plus 1, and we end up getting minus 2 over 1, which is minus 2. We would get exactly the same thing. We plugged 0 into the original function. And for the x-intercept, we'll just set y equal to 0. So we end up with x minus 2 over x plus 1 equals 0. A fraction is equal to 0 where the top's equal to 0, so x minus 2 is equal to 0. So x is equal to 2. So now we have our x-intercepts and our y-intercepts. We can already see from our factorization up here that we have a vertical asymptote where the denominator equals 0 at a place we weren't able to cancel it with the numerator. So we have a vertical asymptote at x equals minus 1. We were not able to cancel the x plus 1 with anything in the numerator, whereas the x minus 1 we were able to cancel. We have a horizontal asymptote. Since the numerator and the denominator have exactly the same degree, the coefficient in front of the numerator, in front of the largest power of x in the numerator is 1. The coefficient in front of the largest power of x in the denominator is also 1. So we have a horizontal asymptote at y equals 1 over 1, which is 1. So let's see. We have our x-intercepts, our y-intercept, our vertical asymptote, our horizontal asymptote. We know we have a hole in the curve at x equals 1. I guess we are good to try to graph this thing. So let me draw in some axes. So we'll label our axes x, y. We'll put a scale on our axes. And we have a vertical asymptote at x equals minus 1. We have a horizontal asymptote at x equals 1. We cross the y-axis at minus 2, so it goes through that point. We cross the x-axis at x equals 2, it goes through that point. We approach this line asymptotically and this line asymptotically. We already have 2 points on the curve. We know we have a hole in the curve at x equals 1. If we didn't have a hole in the curve at that point, if we plugged in 1 to this equation, we'd have 1 minus 2, which is minus 1 over 1 plus 1, so minus 1 over 2. We'd be at height minus 1/2, so we have a hole in the curve right there. Let's see if we can sketch in the function over here. So it has a hole in the curve there and approaches this line asymptotically and this line asymptotically. And over here we can pretty much guess that it's the mirror image. I think we have a pretty decent picture there. We can take a look at part C. Now part C has an oblique asymptote in it. I might as well just show you how to do this. Let's go ahead and take a look at all x and y intercepts again. So there's really no factorization to do here, no canceling to do, so we won't worry about that. We can tell that this thing has an oblique asymptote because the numerator has degree 2 and the denominator has degree 1. And whenever the numerator has degree exactly 1 higher than the denominator, we definitely have an oblique asymptote. So let's go ahead and, as I said, take a look and see where the x and the y-intercepts are. So we have our y-intercept. We'll set x equal to 0. So we end up with y equals 0 squared over 0 minus 1, which equals 0 over negative 1, which is equal to 0. Our x-intercept, we'll set y equal to 0. So we have x squared over x minus 1 equals 0. A fraction is equal to 0 when the top's equal to 0, provided the bottom isn't 0 there too. So we have x squared equals 0, or x equals 0. So this thing only touches the axes at x equals 0, at y equals 0, and x equals 0. Now let's take a look at the asymptotes. We definitely have a vertical asymptote at when, x minus 1 equals 0. In other words, at x equals 1. That's the only place we have a vertical asymptote. We know it's not a hole in the curve because we can't cancel that x minus 1 with anything in the top. And we have an oblique asymptote. To find the oblique asymptote, we actually have to do the division. So x minus 1 goes into x squared plus 0x plus 0. I'm putting in the x term and the constant term. So x goes into x squared. Now, don't expect this to come out even. That's the whole point. So x goes into x squared. X times x is x squared. X times minus 1 is minus x. We're going to subtract. So 0x minus negative x is x. Bring down the 0. So x goes into x one time. 1 times x minus 1 is x minus 1. And we're going to subtract. The x's cancel, and we are left with 1. So what that means is that x over x minus 1 is equal to x plus 1 plus this number, so 1 over the original denominator, x minus 1. You can still see the vertical asymptote right there. This, by the way, is your oblique asymptote. So we have an oblique asymptote at y equals x plus 1. So we're pretty much ready to graph this thing now. Let's draw on some axes. So we said we had a vertical asymptote at x equals 1. We can put that in. We have an oblique asymptote, y equals x plus 1. That's just a straight line going uphill 45 degrees with y-intercept 1. So we can dot that in. We saw that it crossed both the x and the y-axis at 0. And it approaches these two lines asymptotically. So we pretty much have all the information we need to be able to graph this thing. It's going to look something like this. Approaches these lines asymptotically. And we have its mirror image up here. Again, something with an oblique asymptote, that's a little bit different. If you're in a semester where we haven't talked about oblique asymptotes, you wouldn't have to do a problem like this on a test. If you're in a semester where we have, then here's good practice. Let's take a look at the next question. So we're going to express the number y equals, we're going to express the number 1 over 2x plus 2 plus 3i in the form a plus bi. And I put a little cautionary note here. We know how to do a question like this. We know how to divide a numerator by a denominator like this, where the denominator is a complex number. We write 1 over 2 plus 3i, and then we are going to multiply both sides. We're going to multiply the top and the bottom by the same number. In other words, multiply by 1. So times. We're going to multiply the numerator and the denominator by the conjugate of what's here. The conjugate of 2 plus 3i is 2 minus 3i. We multiply by that on the bottom and on the top. 2 minus 3i. On the top, we end up with 1 times 2 minus 3i, which is just 2 minus 3i. And in the denominator, we have 2 plus 3i times 2 minus 3i. Let's FOIL that out. 2 times 2 is 4. 2 times minus 3i is minus 6i. 2 times 3i is plus 6i. So the minus 6i and the plus 6i cancel out. And then we have 3 times minus 3, that's minus 9. I times I is I squared. I squared we know is negative 1, so that is 2 minus 3i all over 4 plus, so minus 9 times minus 1 is equal to plus 9. Remember, 9 minus 9 and I squared is minus 1, so minus 9 times minus 1 is plus 9. And so I have 2 minus 3i all over 4 plus 9, which is 13. And that's equal to 2 over 13 minus 3 over 13 times I. Now we're down here. We're supposed to find all the roots, real and complex, of x cubed plus 8 equals 0. So let's go ahead and do that. We know that if this has any rational roots, p has to divide 8 and q has to divide 1. It doesn't take us very long to spot the fact that 2 works. So if I write p of x equals x cubed plus 8, then p of minus 2 is equal to minus 2 cubed plus 8, which is minus 8 plus 8, which is equal to 0. So one of our factors is of x cubed plus 8 is definitely x plus 2. And now to get the other factor, we have to do long division. So x plus 2 goes into x cubed plus 0x squared plus 0x plus 8. So x goes into x cubed, x squared times, let's do our multiplication, x squared times x is x cubed, x squared times 2 is 2x squared. We're going to subtract. So that leaves us with a minus 2x squared here. We'll put in our plus 0x. X goes into minus 2x squared minus 2x times. Minus 2x times x is minus 2x squared. And minus 2x times plus 2 is minus 4x. We're going to subtract. That leaves us with a 4x. So that's still visible. And we're going to bring down the plus 8. X goes into 4x 4 times. 4 times x plus 2 is 4x plus 8. We have a remainder of 0. So x cubed plus 8 is x plus 2 times x squared minus 2x plus 4. And now to get we already know that x equals minus 2 is a root. So x equals minus 2 is one of our solutions. To get the other two solutions, if we're going to set this equal to 0, we can use the quadratic formula on that. So let's go ahead and do that. So x equals, so we're just doing this part now. So negative b, that's 2 plus or minus the square root of b squared. So minus 2 squared is 4 minus 4 times 1 times 4. So 4 times 1 times 4 all over 2 times 1. And that equals 2 plus or minus the square root. 4 minus 16 is minus 12 all over 2. And we can rewrite this as 2 plus or minus 2 times root minus 3 all over 2, and this equals 1 plus or minus root 3i. So minus 2, and then 1 plus root 3i, and 1 minus root 3i. Hopefully that's all visible. All right, let's take a look at the next page. So, question number 5. There we go. So a box without a lid is constructed from a 4-foot by 6-foot rectangle of cardboard by cutting out equal squares of side length x from each corner and folding up the flaps. Express the volume V of the box as a function of x. So let's draw ourselves a little picture here. We start off with a 4-foot by 6-foot rectangle. So we'll write 6 feet right here and 4 feet right here. And we're going to cut out squares of side length x. It's supposed to be a square. Another square over here. Another square over here. Another square over here. We're going to take these out entirely. So that's length x, that's length x, 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 x. We're going to fold up the sides. So we have 1, 2, 3, 4 flaps that become the sides of our box, and this becomes the bottom of the box. And we know that the volume of the box is just going to be the length times the width times the height. So the length of the box is just going to be from here to here. We started off with 6 feet, and we subtracted off an x over here and an x over here, so that's 6 minus 2x. The width of the box is just going to be from here to here. We started off with 4 feet, and we cut off x and x, so the width of the box is going to be 4 minus 2x, and the height of the box is just going to be the height of each of these flaps, in other words, x. So the volume V, we already defined V in the problem, so V is equal to length times width times height. So we said the length of the box is 6 minus 2x, the width of the box is 4 minus 2x, and the height of the box is x. And you can multiply that all together if you want to, but this is fine. And now we're supposed to find the domain of the volume function. So what's the biggest and the smallest values that x could take? Well, x certainly cannot be negative. I mean, we're cutting out a length there. The length can't be negative, so the smallest x could be is 0. The biggest x could be, that's a little bit trickier. You can see that we start off with a box of width 4. If I cut off 2 feet over here and 2 feet over here, these two squares actually touch. And if I cut off anything bigger than 2, they overlap, which doesn't make sense at all. So the biggest that x could be is 2 feet. Now you could make an argument that you can't really include 0 and you can't really include 2, and that would be fine, but I'm going to include them just to, I certainly wouldn't take off points if you said it was the open interval from 0 to 2. But I'm going to include them for reasons which make a lot more sense once you've gone through your calculus class. Okay, so now let's take a look at the next question. The concentration of a certain steroid is monitored in a patient's blood after a treatment is given. The concentration C in milligrams per milliliter, T hours after the treatment is described by the following formula: 2x squared plus 3x plus 1 over x squared plus 1. What's the concentration of the steroid in the blood at the time the treatment is given? Oh, I see a problem with this problem. It says x here, but actually the time is in hours t. So this should read 2t squared plus 3t plus 1 all over t squared plus 1. I put in x's when I should have put in t's. What's the concentration of the steroid in the blood at the time the treatment is given? About 1 hour later? So when the treatment is given, I'm going to plug in t equals 0. So t equals 0. So C of 0 is equal to, can you still read that? So C of 0 is equal to 2 times 0, which is 0, plus 3 times 0, which is 0, plus 1, all over 0 squared plus 1, so that's 0 plus 1. So that's 1 over 1, that's 1. Let's put on units. 1 milligram per milliliter. And now let's take a look 1 hour later. I'm just going to plug in t equals 1. So C of 1 is equal to 2 times 1 squared, that's 2, plus 3 times 1, that's 3, plus 1, all over 1 squared plus 1. So that's 1 plus 1 at the bottom. So 2 plus 3 is 5, plus 1 is 6. So that's 6 over 2, which is 3 milligrams per milliliter. Now, as t becomes large, what happens to the concentration of the steroid in the blood? Explain how we know for sure. Well, let's take a look at this question right here. Well, actually, let's take a look at it with the t's in there. So here's how it should read, even though I mistakenly put x's in the original question. So we can see that the numerator and the denominator have the same degree. They're both degree 2. So this has a horizontal asymptote at a particular height, which we can find by taking a look at the coefficient of t squared on the top and the coefficient of t squared on the bottom, so 2 over 1. So that means we have a horizontal asymptote at height 2, which means that as t gets very big, we get closer and closer to height 2. So coming back down here, as t becomes large, C of t approaches 2 over 1, so that's 2 milligrams per milliliter, and we want to explain how we know for sure. We know that C has a horizontal asymptote at height 2, and that's how we know. Okay, let's take a look at the next page. We're starting to move into questions that we're taking a look at questions that deal with trigonometry. So find the length of an arc with angle 45 degrees and a circle with radius 2. Well, our very first job there is to turn that angle into radians. So 45 degrees times pi divided by 180 degrees, and that equals pi divided by 4. And now we can find arc length S very easily. S equals r times theta. So in this case, 2 meters times pi over 4. And so we have 2 pi over 4 meters, or pi over 2 meters. Find the area of the circular sector with angle 45 degrees in a circle with radius 2 meters. So again, theta equals 45 degrees, which again is equal to pi over 4. And we already know the radius is 2 meters, so r equals 2 meters, as it was in the previous problem. And now we have that the area equals 1/2 r squared theta. So that's 1/2 times 2 meters all squared times pi over 4. And so this is 1/2 times 4 meters squared times pi over 4. I guess this 4 and this 4 cancel out, and we have pi over 2 meters squared. Now let's move down to some questions where we have to solve. So we're going to find all solutions for the following equations in the interval 0 between t is between 0 and 2 pi. Let's see, can we get this on the screen here? So let's sketch ourselves a little graph of sine. So we're just going between 0 and 2 pi. We know sine goes between height -1 and 1. Sorry, the axis isn't very straight there. Let me see if I can straighten that out a little bit. So let's sketch in pi over 2, pi, 3 pi over 2, 2 pi. That's the interval we're given. And the sine curve looks like this. So up, down, and back to the middle. We can see that sine x equals 0 1, 2, 3 times. So x is equal to 0, or pi, or 2 pi. And that's all for that. Now let's take a look at cosine of x equals √3 over 2, well, minus √3 over 2. So we'll take a look at the cosine curve. This is not the only way of doing this. So the cosine curve starts at the top. And ends at the top there. It's at the bottom here, crosses the axes here. So this curve looks like that. And we can see that there are going to be two answers. Minus √3 over 2 is about there. So we're going to have a solution somewhere between pi over 2 and pi, and another solution somewhere between pi and 3 pi over 2. The best way to figure this out is to go ahead and take a look at the unit circle. So let's sketch our unit circle here. We know for a general point on the unit circle, cos describes the x-coordinate, and y describes the sine describes the y-coordinate if our angle is theta. So root 3 over 2, that should look very familiar. We know that cosine of 30 degrees of pi over 6, so if this is pi over 6, we know that cosine, so this point right here, is cosine pi over 6, sine pi over 6, oops, sine pi over 6, and cosine of pi over 6 is root 3 over 2, and sine pi over 6 is 1/2. So this is the x-coordinate, this is the y-coordinate. So we want minus root 3 over 2, that's way over here, that's with the opposite x-coordinate. So let's see, that makes that pi over 6, and if that's